Right. So we left the previous lecture, so this is for those that watch this online. This is the earlier lecture on introduction to approximate Bayesian inference. What slide was the other one I had? You forgot. Okay. We relocated. So we're going to continue on that earlier lecture. There was this Ising example that I went rapidly. So let's review it because it's very fundamental to lots of areas. All right. So obviously you have worked on this in the homework. We assume here we have some observations y that are defined, let's say pixel y's, and x maybe are the, so this is an image, this is some noisy version of the image, and these are the original pixels we try to estimate. So there is no z here, so you can think the unknowns basically are x. This is what we want to do an inference. And so we work with the joint and the posterior. We put some prior. The prior is basically standard for this type of images. Gives like distribution e to the minus E0, some energy functional that accounts for nearest neighbors, basically interactions. Okay, this is sort of very typical of these Ising models. These are some coefficients given here, xi, xj, they're binary variables, plus minus 1. Okay? All right, so we write the likelihood locally as the product for all i's of yi given the probability of yi given xi, and we write this probability so we can make the algebra to look nice as e to the power li. So the total likelihood basically is the exponential of the summation of these energies li of xi. Okay, so that way we can write the posterior as e to the minus some energy, where the energy is E0 minus the summation of the local evidence, basically. Okay. So what we want is, we want to compute an approximation to this posterior. All right, that's our objective. I mean, you can, this is an easy problem. You can directly work with this, so you don't really need an approximation. This is an easygoing distribution, but we say, well, you know, we want to factorize q of x in a nice form that is factorized over I. All right, so for each I, we're going to have a corresponding q I of xi, and because xi is plus minus 1, is discrete, the only thing we need to describe each of these distributions is the mean value. Okay? All right. I remind you now the fundamental equation that we derived for each of these factors. So you have to remind me. So we did the derivation analytically, and we said each factor qi, or the log of each factor qi, is equal to what? The expectation of so each of these factors, this fundamental 12 variation problems, each factor qi is log of qi is equal to I mean, I can go outside the room, take a break for 1 hour until you guys tell me what the formula is, whatever works. So log of qi, I mean, I should have put an index there, qi, but it's obvious from the argument. So log of qi is equal to the expectation of what? Of what? You know, as you get older, you hear less. But it's by design. You want to remove all the noise. All right, so log of qi equal to the expectation. Why are you looking at me? You know, I mean, either it's there or it's not. First of what distribution? We have the expectation of the log of what distribution? Before, when we derived in general, right, we had observable x and we had latent variable z. So what distribution the right-hand side of the equation was referring to? The joint log likelihood, right? That was the starting point. So the joint log likelihood here is basically this, all right? So we said that each of these factors really is nothing, the log of each of these factors is the expectation of this joint log likelihood, which is basically minus this energy. You take the logs, this is, we're talking about the anormalized thing here, so it's minus the energy E of x. So, so the log of the joint log likelihood is obviously E0 is this, right? So with a minus sign, it will be xi times the summation of all the neighbors of I plus Li of xi, and I wrote it plus many more terms, and I wrote it this with xi to be apparent. Why? Because I'm going to set the log of qi, which is a function of xi, right, equal to what? The expectation of this, and I want to identify only the terms that depend on xi, right? There are many more terms, but they will not make any difference in the context of xi. All right, and now we have to define the log of qi. We're going to have to take the expectation of this with respect to what? We derive the fundamental equation in variational methods, right? The log of its variational distribution qi is the expectation of this joint log likelihood with respect to what variables? Mean field approximation. All others but xi. So when you take the expectation of this with respect to all other variables, you're not going to touch xi, right? Because it's all other variables, but these xj's, you're going to substitute them with what? By definition, with their mean values, because take expectations of what is the mean values of xj is mu j. All right, so we said that the log of qi was equal to that, so qi is the exponential of xi times the summation over the neighbors of I plus the local evidence that depends only on xi. All right, because xi can only take values plus 1 and minus 1, so I'm introducing two different definitions here. Li plus is the value of Li when xi is equal to 1, Li minus the value of Li when xi equal to minus 1. And the reason I do this is because since xi is a discrete distribution, I am going to calculate the variational approximation qi at xi equal to 1. So look at this formula. This is a normalized distribution, right? That's why you have this symbol here. Do you agree that qi for xi equal to 1 is equal to really, let's call this whole summation here mi. All right, so this whole summation, we're going to call it mi. So will you agree that qi for xi equal to 1 is, this would be 1. So e to the mi plus xi equal 1 plus li plus divided by this normalization factor. Right? Okay. If I rewrite this, I can do it like this, and immediately you see that this qi of xi equal to 1 comes to be a sigmoid. Okay. So that's a very nice result. Okay. And similarly, the value of qi for xi equal minus 1 comes to be the sigmoid for argument minus 2 ai, where ai is this nice term here. Mi that we said is the summation, known because these are the means of the neighbors, plus 0.5 Li plus minus Li minus, also known. So the mean value of the discrete variation distribution of xi is basically qi when xi equal to 1 times the value is 1 plus this times when the value is -1. And if you substitute all of these things, you get that the mean values is it's the hyperbolic tangent basically of AI. Okay? Also a very nice result. And so the update formulas, basically, if I can write this explicitly, is that the mean value of every variable I is the hyperbolic tangent of what you see inside this parenthesis. Obviously, to update mu I, you need to know the mean of the neighbors. So this equation can only be solved in self-consistency, right? So you have to iterate, and obviously you can do this with a lot of nice tricks. You can go through each of the pixels and repeat this until basically converges, or you can do it even in an asynchronous manner, okay? So the iterations look like this. So if you put an index t here for the iterations, you use the previous whatever values you have, you update mi, and you keep going. And then more often you will see this in, if you download programs that do this, you actually apply this equation with some relaxation. So rather than using this value for mu I, you use a convex sum basically of the previous values plus the value that is predicted through variational methods, okay? So this is sort of way more stable and avoids a number of effects that usually are common in Ising models. All right, so I gave you an example, and the example is basically you can run it. It's in Murphy's Toolbox. The only thing you have to do is once you install it, you just put Ising image denoise demo, and it will get you all the results, and you can see the nice program, only 10 lines that can solve this little problem, okay? So this is effectively you start with a noisy image. You know, obviously you have to need to use some parameters. For example, this parameter lambda in this relaxation method is half, you know, but you can see immediately the methodology is able to recognize what the actual image is. And so this is the mean of the posterior, of the Bayesian posterior, after a number of 15 strips through all the pixels in the image. All right. So I'm going to be, you know, there's way too much material to be covered here, and this is an important topic, so I need to be sure that we discuss more or less the most important things. So I'm going to jump on the slides and go to slide 38, and then remind me to come back to slide 31 once we're done. So let me do another very simple example. Unless we already have done it, we will do this example with a Gaussian. Okay, if you figure out that we did it, just let me know, okay? Because I'm doing too much jumping here. All right, so let's suppose we collect data from a Gaussian that has a precision tau and a mean mu that we don't know, okay? And so the typical Bayesian inference problem is to calculate the posterior of mu and tau. And again, for those who have taken Bayesian inference courses like the course in the fall, there is an analytical calculation basically that gives you the posteriors exactly. But what I want to do is I want sort of to use the variational method so we can see how they work and how good they do. So I'm going to take the priors on mu and tau to be what's called a normal gamma distribution. So given tau, the distribution of mu is a Gaussian, and then for the precision that comes also in this distribution, you put a gamma distribution as a prior. Okay, so this is the priors, and for these priors and this likelihood, there is an analytical solution for the posterior. We pretend we don't know what that solution is. We don't really care right now, And what we want to do is we want to calculate the variation posterior, and using the mean field approximation, we're going to factorize it. The joint is going to be written as some variation distribution of mu and some variation distribution of tau. By the way, we immediately see that this is going to be an approximation, right? Because for those who have looked at this problem before, the exact solution, you expect basically if the priors look like that, this is in the exponential family, the posterior is going to be on the exponential, it's going to be a Gaussian gamma, for example, for mu and tau. So you expect the posteriors for mu and tau to have this form, where instead of mu 0, lambda 0, and alpha 0 and b 0, you have some mu n and lambda n and alpha n and bn for n data points. Obviously, this doesn't fit in that form because the distribution of mu does not involve tau. It's an approximation. So it's, we do it to see, if things make sense, right? Obviously, you are not going to do this in reality, okay? But in this class, there's no reality. Correct? Yeah. All right, so this is an analytical formula. The optimal Qj is the expectation with respect to all the other variables, so the log of the joint log likelihood. So I am going to start playing with this, and this is a calculation you need to get really to understand it, all right? Because you will not, if you don't understand it, you will never see it, you will not make any sense of these derivations in literature on many infinite settings, okay? So you have to work through these little problems. Okay, so let's say we want to, let's update the variation distribution for mu, okay? We're going to take expectation with respect to all the other variables. There's only one other variable, which is tau. So here, the joint log likelihood, it would be the likelihood of the data, all right, which is Gaussian. You remember there's a prior, and there's a prior on mu given tau, and a prior on tau, but since we're interested in the distribution of mu, any term that does not depend on mu we don't play with, okay? So the prior on tau is what I call constant. So if you expand this, you're going to get something like this, right? Since we're interested in mu, that's the only term we keep. If we expand, let's see, can somebody tell me from where did this thing come from? Where's this term coming from? So this came from the likelihood there, all right? Okay. And where is this term coming from? Prior of mu given tau, okay, which is Gaussian, okay? You remember the precision of that? It was lambda 0 times tau, so obviously you're going to get lambda 0 times tau, but the tau became expectation of tau. Why? Because everywhere there is any tau, we need to take expectations. Okay? And again, the rest terms that depend only on they don't depend on mu, we don't include them. Okay, so you look at this, nice. What type of distribution do you think you will get here if you play for 5 minutes with this calculation? I mean, we need a distribution of mu, and I see mu squared and mu squared, and a linear term in mu and a linear term in mu plus constant. So obviously, closing the square, you're going to get a Gaussian distribution, and this Gaussian distribution you can solve with 0 time, has this mean and has this precision, okay? And so X is the sample mean, basically. This is where the data come from. This comes from the prior. Lambda n involves the precision of tau, and immediately that reminds you, because we don't know yet the posterior of tau, that somehow we're going to need to do iterations. So basically, to compute this distribution, you need to know what the mean of tau is, okay? So we need to go and compute tau. So similarly, let's do tau. Again, we have to take expectation with respect to all the other variables, which here is mu, of the likelihood, the prior of mu given tau, and the prior of tau now has to be included because we're interested in the distribution of tau. So this term comes from the data likelihood. So obviously there will be an expectation with respect to mu. This comes from this. So there's going to be an expectation with respect to mu. Where is this thing coming from? Where are those two terms, the first two terms coming from? The prior of P of tau, which is a gamma distribution, all right? And where are those two terms coming from? Remember when before we play with this distribution, okay, we only kept the terms that involve mu. Here we have to keep all the terms that involve tau. So can you tell me where, let's say the easy term, where is this term coming from? So let me go back for you to remind you everything. So where that n over 2 log of tau comes from? From the likelihood. And you notice there's another tau term coming from there, all right? So where is it? Okay, so we have this term plus this term. So effectively what you need to do, if you look at this carefully, it is the log of a gamma distribution, all right? So in the gamma distribution, when you take logs, you get a log of tau and a tau term. So if you put all the logs of tau together and all the tau terms together, all right, what you will get is you will get a gamma distribution for instead of alpha 0, you will have alpha n, and instead of b0, you have beta n. And again, here you need to have expectation with respect to mu, and don't need to do all of this. So basically this distribution summary of everything, Q of m is a Gaussian, Q of tau is a gamma distribution. The parameters are defined the way you see them here. You can see to define the mean and the variance of Q of m, you need to know the mean of tau. In the mean of tau, you remember for a gamma distribution, what's the mean? If I have a gamma distribution with parameters alpha and beta, what's the mean? Anybody remembers? Alpha divided by beta, all right? So you can see immediately that the mean of tau depends on alpha n and beta n, which again depends on moments of mu, all right? So you need to know the distribution of mu. So effectively what you need to do is you need to iterate, okay? It's like you start with some values of this, then you compute gamma, then you find the moments, whatever the expectation of tau, you go back, you recalculate this, keep going until basically convergence. And here is sort of a little example, I don't know, yes. So there is a Python code written by a former student again, that you can download, and I think this link is corrected, but some of the links I need to double check that they are making sense. So, okay, so this is one re-estimation of this Q of mu. With Q of mu updated, you update Q of tau, and then when it converges, it approaches the actual distribution that you see with this, I am assuming red or green curve, okay? All right, so this again, it's a trivial example, right? We know the analytical solution, but if you think about it, the cost of doing this calculation is trivial, and but if there is an analytical solution, unfortunately, you cannot go by but using only the analytical solution. And if there is an analytical solution and you pretend you don't really know, that's very bad for you. Okay, so you need to know. Okay, but in this problem we did it sort of exercise. Okay. All right. So I want to do a calculation that I'm going to repeat for other problems as well, right? When you remember when we started the variational methods, right? We saw that we defined what's called the lower bound, right? And this was a bound to what entity? To the likelihood of x. Okay? So one of the things you need to do when you write these codes, right, is to actually compute the lower bound. Because the objective in variational inference is to do what? Obviously, you want to maximize the log likelihood, right? And because the log likelihood is intractable, you try to maximize what? The lower bound. So, you really have no choice but to compute the lower bound. So in other ways, if you do all of these iterations, right, you go from one iteration to another, the obvious question is, can you show me if your lower bound actually increases during iterations? Because if it doesn't, whatever iterations you do, it's magic, it's not science. You need to show that the lower bound continuously increases. Okay? So we need to compute the lower bound. That's a standard calculation you have to do in this approximate variational methods. So let's do the lower bound for the simple case of the Gaussian. So I'm going to remind you, the calculation, it's algebra, but it's standard. If you do it 2 or 3 or 4 problems, you will be able to actually do this in research-related problems in machine learning. Okay? So the lower bound, I remind you, is the expectation with respect to the variational distribution, Q of mu and T, which we factorize it, and of the log of the joint log likelihood, and I wrote it here explicitly. This is my data D, mu, and tau, divided by the variational distribution, and then mu and tau integrate tau. All right, this is the definition we use. That's the lower bound. So if you expand this, all right, so I'm going to remove this Q and substitute it with expectation of the arguments, right? This is the expectation of this log with respect to this variational distribution Q. So that's what E refers here. So I have the expectation of the log of the numerator, which I can write it the log of the likelihood given the parameters, and then I have the prior log of the prior of mu given tau and log of the prior of tau. You see that? This comes by writing this as the likelihood times the prior. Right? Nothing else. And then the denominator, because this is factorized, I have expectations now, these expectations of the log of Q of m and a log of Q of tau. We agree? All right? So what you need to do, you need to go and compute all of these terms. Okay? It looks a massive task, and this is only a univariate Gaussian, so you should be able to live with it. Okay, so let's see. Let's pick up the easy terms. If you take log of Q of m, what type of distribution we said Q of m is? It came to be a Gaussian, this Gaussian here, right? So when you have the obviously there is no tau here, all right? So the expectation was with respect to mu and tau, but this now becomes the expectation with respect to mu. So really, what you have here is nothing else but the entropy of this Gaussian distribution. So you can look in Wikipedia and say entropy this, there's the answer. Okay? All right, so this is the entropy of this variational distribution. Similar for ln of Q of t would be the entropy of the gamma distribution. You can, again, look at Wikipedia. I look every 5 minutes when I check these things right. There is information everywhere around you. In case you don't remember, this is what's called the bi-gamma distribution that appears in the gamma distributions. It also appears in Dirichlet distribution. So this is the bi-gamma distribution. Okay, I'm not going to tell you what it is. You can look, and I trust there is a link there on Wikipedia and you should read it. Only think about what poor people and graduate students were doing 30 years ago, that there were no really computers, there was no Wikipedia, there were no books, there were no PDFs of Chinese origin or anything like that. Everything, it was nice and clean somewhere in some library, and you have to go and spend 5 hours to locate it in a library. Here, 2 minutes, there it is, all right? But obviously, if you're given something immediately, means the expectations that you do something with that are higher, all right? Because this is the information era. You need to use information, no excuses for not knowing things. All right, so let's see more complicated terms. We need now the expectation of the log of pi of t with respect to q of t. So I keep the expectation outside. I'm expanding the log of a gamma distribution. So there is nothing here. These are from the normalization terms, okay? This comes from, you remember the gamma distribution is tau to alpha 0 minus 1, tau to minus, to minus beta 0, right? Or beta 0 to minus tau, what was it? Yeah, okay, something like that, okay? So, okay, so let me see, there must be a missing term here. So I need to take expectations this with respect to q of t, okay? And this term is constant, this term is constant, okay? What you need to do now is you need to take expectation of the log of tau with respect to q of tau, and q of tau is what distribution? Is gamma. So if tau is, this is a very famous formula that comes very often actually in machine learning. If tau is a gamma distribution and you have expectations with respect to the gamma distribution of the log of tau, the result is that by gamma distribution calculated on, so the gamma distribution has parameters A and B, so it's psi calculated at A minus log of beta, okay? And somehow you also need to compute the mean of a gamma distribution, which is A over beta. So basically, you're done with this term as well. This is trivial because this is Gaussian, this is Gaussian. So I am just giving you the results. If you expand, okay, and you use the sufficient statistics of the data to simplify, you get these nice results. Similarly for this, it's a Gaussian. Okay, you expand, and this is the final formula, okay? It looks very complicated, and you may ask me, am I so kind to you putting all these things in different colors? No, you know why I'm putting them in colors? Because when I was deriving this, I kept doing mistakes, so I wanted to know what combines with what, so I was doing it for myself, because, this is the only way I can learn, right? Now, if you want to take advantage of the colors too and figure out why they were there, okay? So these terms obviously would be the same color combined, and when you finish, you get, let me see if there is you get actually an extremely trivial formula, okay? I'm surprised myself too. Obviously lots of cancellations. The lower bound is minus 1/2 of ln of lambda nu, okay? Plus log of the gamma function computed at an minus an log of bn. And I remind you these an and bn's, we defined them when we computed the variational distributions. So basically L of q, it's one line of a formula. So what you need to do is, as you update these lambdas and alphas and betas in the two variational distributions, you actually have to plot this L of q and be sure that is monotonically increasing. If it is not, either the calculation of the distributions is wrong, or basically your calculations of the lower bound is incorrect. Okay? This is very essential. You have to do this in every problem. All right, so let me, since we talk about, for the single Gaussian, about computing the lower bound, right, to see that we optimize properly, let's discuss a little bit variational inference and variational approximations in the context of model selection. And I believe in this class, at least, I have not talked at all about model selection, but we spent lots of times, lots of lectures on in the fall to discuss about model selection. So the idea here is, you may have different models that you label them with M, all right? Maybe you put some priors on these models, and you have some data, and you want to figure out what is the best model, all right? What's the best model? So the question is, can you actually use variational optimization, variational inference to find the best model? So in principle, what I'm asking is, will it be possible, let's say you start with some prior that is even, let's say, an informative, you put the same probability in all the models, can you calculate, given some data, a variational posterior of M, where M is a model? So if you have 5 models, what's the best model, right? And we will do this, in the context of regression, I think, possibly today, right? But I wanted to do sort of a very trivial calculation to see if variational calculations can actually be used to compute a posterior of M. All right, so basically what we're looking here is, if we have some data X, right, can we calculate the posterior of a model given the data? And I mean, you can think in general, for example, if the model is, say, it's regression, maybe model M equal to 1 is you use linear functions. Model equal 2 is you use quadratic functions. Model equal 3, cubic functions. Or maybe, model 1 is you use 1 basis function, model 2, 2 basis functions, 3 basis functions. Which model does the best? All right? And obviously, we know the model that maximizes the likelihood will be of interest, but we have to see formally how these calculations come in the context of these variational methods. So I want to do some simple, trivial, nothing sophisticated here. So what I'm going to do is, let's say that every model has its own latent variables. So don't expect the latent variables to be the same in every model, right? Every model we have different variables, different discretization, different parameters. So, so when I try to define a variation approximation of the posterior of Z and M, I am going to write it as follows. Some variational distribution of Z given M. So this is an approximation of the posterior of the Z variables from model M times the posterior of model M. All right, so nothing specific. All right, so let's just do some trivial calculations here to see how this whole things come together as an approximation to the log likelihood without any discussion of models there. All right, so what I have done is I use the definition of the lower bound. All right, and the lower bound, you remember, was the expectation with respect to the latent variables, and in this case the latent variables is really Z and M. They are both unknowns, okay? And I put a posterior, this is my approximate posterior, this is the expectation part, and then I have the log of the joint log likelihood. Notice the log likelihood is my real data is X, my Z and my model. Because I have enhanced now, I have put the model to be an unknown. This is averages basically over all models, okay? And then on the denominator, I basically have the same variational distribution. So you can write the same as before. So here what I do is I write the exact posterior of Z and M given the data times P of X, and this like that, okay? And in this last line, what I do is I take this P of X and I remove it out because it doesn't depend on M and Z. So effectively what I get is this nice thing plus log of P of X. And if I rewrite it, log of P of X is basically the lower bound minus this. Okay? Does this remind you anything? What is, remember when we had the fundamental identity that the log likelihood is equal to the lower bound, and what else was there? The KL divergence. The only difference here is, instead of having the posterior of Z, I have the posterior of Z and M. Right? So nothing really has changed, okay? But I haven't really been very much informative to tell you on how you compute Q of M. So let's see what we can do this. So what I'm going to do is, if you have different models, let's say, you can maybe go and do variational approximations on each model, and you can go and calculate the lower bound for each model. So Lm is the lower bound for model M, and I write it like that. Everybody agrees? I mean, you can see here, what is that? Is the joint log likelihood for model M. There's nothing fancy, okay? I condition everything on M, basically. All right. So the question is, once I have this, can I come up with an overall lower bound, basically, for my whole problem, where models have been integrated out? So let's see how the calculation looks like. It's actually a very interesting algebra. So this is what we started before, all right? This is having a variational distribution of models and all the z's for each model. So what I do is I write the actual joint log likelihood here as the probability of z and x given M plus the prior of M, all right? And then on the denominator I have minus log of Q of zm and Q of M, all right? Let's see, I see here, I'm going to pull Q of M outside, okay? So Q of M goes to the whole thing, so I'm going to pull Q of M outside. So I have Q of M, ln of PM, nice, ln of QM, nice. I have, obviously the summation on M will remain outside. Then I have a summation on Z, and this thing, all right, depends on Z. So I'm going to have Q of Zm, ln of P of Z, comma X given M, and we have this term as well. Will you agree that this whole thing, it is really Lm? Compare it with that. Is it? It is, right? All right, so I'm writing this whole thing then as Q of M log of P of M minus log of Q of M. And here I have Lm, so I write it as log of e to the Lm. Right? Nothing spectacular. There's a reason for this. I write it like that because then I can write this whole, the overall lower bound, I can write it as Q of M, ln of P of M times C to the Lm divided by Q of M. And so look at this nice now derivation of the lower bounds and tell me what is this nice quantity? What does that remind you? By definition. Come on. I see Q, and then I see something there. It doesn't have to remind you, oh, it's this quantity of something we have mentioned, maybe something we have not mentioned. But what is this by definition? The what? I don't hear a thing. Remember noise filtering? And it's nonlinear filtering. All right, so what is that entity? Is minus the what? I know it looks like an expectation, but there is a better definition of what is this. Is minus, I gave you half of the story. Minus of the KL divergence between Q and P of M times e to the Lm. All right? So if the overall objective is to maximize the overall lower bound, then you have to minimize, this, and we know the exact answer, right? This will be optimized when Q of M equal to P of M e to the Lm, where Lm is equal like that. So really now, for the first time, in only 2 slides, you have seen a variational posterior over models in 2 slides. Okay? So you can start, this can be extremely useful, right? If you want to do model selection in regression, in classification, just mention it, all right? You're going to, at the end of the day, you're going to put some prior over models and say, you know what, which model does the best, all right? So this gives you an approximation, given some data of the posterior over models, and if you plot this for model 1, 2, and 3, etc., you will eventually be able to do model selection, figure out what's the best model that interprets the data. Okay? So this is a very nice calculation using variational methods that extends basically these concepts for computing distributions over latent variables, now computing distributions over latent variables and models. All right, so very nice. All right. I'm debating now if I should. So there is, on this lecture, the way I have it, there is another topic that's a little bit more complicated than the topics to come, but because I somehow put them together, let me finish it up, right, and try to do our best to understand it. All right. So again, this is a little bit ahead of, it's a little bit more difficult than some of the problems we will see next, but let's get it out of the way, okay? Or at least in spirit as to what the methodology is about. So what you see here is a hidden Markov model where, it's in the slides, this, in earlier lectures. The difference from what we discuss in most of the presentations on HMM is that we have multiple chains, that they're linked together, and they're linked together, as you can see, because the observations at every time depend on the state of all the chains. Okay? So if you try to actually do forward, backward messaging and, these alpha and beta messages, you're not going to be able to do it because the chains are coupled. Okay? So this would be a serious limitation of the things we learned in the context of what's called factorial hidden Markov models, okay? So what I want to highlight basically today is can somehow use some ideas from variational methods and do some approximation of the posterior of this stage of the different chains in a way that somehow uncouples them in a manner that somehow will allow us to use forward, backward message propagation the way we have seen it for one chain in the past, or for independent chains. So we need to see if variation methods actually are of any use on this problem. I mean, variation methods, we will see they are of use to everything. Okay, they're approximate methods for everything. All right. So let me write first the exact joint log likelihood. So you can think here my z variables is really x. Right, this is the unknown states. The data are y. You can see here marked. So the joint likelihood is basically my transition model from t minus 1 to t, okay, and the observation model, okay. And you notice there is a coupling here, and I'm going to show it to you explicitly because yt depends on the axis on all these states. X, M, right? And this is a product, the joint log likelihood, joint likelihood is a product over the chains and all the time instances T. Okay? So the definition is basically similar to what we have seen for the exact joint log likelihood that we have seen before. So A, we use it for the transition metrics. We have some probabilities for the initial state. What is different from what we have done before is that there is an index M, right? There is an index M because this transition probabilities and the initial probabilities have to refer to its chain K from K1 to M, okay? That's the only difference. So the likelihood model, this is departure from what we have done in the HMM presentations. It is now, the mean is defined to be estimation of a linear approximation, basically, a linear weighted sum of the states at this time. And the coefficients here, we take them to be given to start with, okay? So the mean is given some linear interpolation between the values of x's for all the chains M from M equal little n equal to 1 to capital M. Okay? So this is the exact model, all right? And it is computationally very difficult to work with because of this equation. So this equation couples things, so you won't be able, if you try to do expectation maximization, for example, and compute the sufficient statistics, you won't be able to use forward-backward message passing because these messages are all coupled, so it would be computationally a very difficult thing to do. Okay. So I am writing the exact posterior, basically using exact joint log likelihood. So I'm expanding it. Basically, this is the log of the probability that we saw in the previous slide. So this comes from the data likelihood. That's where the coupling is. Okay, it's a Gaussian, and we have taken logs. So this vector here is the log of the probabilities of the initial states for each chain M, and this is the logs of the transition probabilities for each state M. There is really nothing new from what we discussed with HMM, except the fact now that I have, instead of having one chain, I have a summation of each state of all the chains with their own initial probabilities, and in the transitions I have another summation of them for all the transition probabilities, right? So we need to find some way to use approximate inference to solve this problem, okay? And the idea is, remember when you do approximate inference, right? The word is approximate. So basically you have to use your intuition and you say, I am going to try something that looks like that, and let's hope for the best, all right? So the approximation we will discuss is an approximation that will decouple the chains. Okay? So somehow we'll decouple them so that way we can run alpha beta messages back and forth basically for each chain independently. Now to decouple them, let me just tell you what the idea here is, right? Obviously the chains are coupled. All right, they're coupled. So we're not going to say, oh, they're independent. They're not independent, they're coupled. So if we try to approximate them as independent, can you imagine in the context of mean field approximation something we need to do to get rid of this term here? This is the evidence that couples everything together. Can you think of some sort of, idea that somehow we would be able, let's say, to do forward and backward message passing on each chain, but we're going to be able to account for the average effect of all the other chains. Right? That's what a mean field approximation is. I mean, each chain does whatever it does, but in the average influence of all the other chains. So we need to introduce some concept of local evidence, not this evidence, but some local evidence that is introduced in every chain that comes from the effect of all the other chains. Make sense? All right? So yes, we're going to run them independently, but there must be something that influences, let's say, chain 1, because these chains are in some state. Okay? So here's the idea. All right? Actually, all the equations you need are on the on those 3 lines. So this local evidence, I call it basically at each time, I call it Xi TMK, all right? So this obviously refers to time t. It refers to chain M, okay? And chain M, because this is an HMM, can be in capital K states. So the little k is what state it is. So can you guess what is CTMK trying to do in this equation here? There is no other evidence. There's no, the y's have disappeared from the picture. There's no evidence or anything like that, right? All the evidence comes from this x's. So what do these x's really are trying to accomplish the way that you see them on this slide? So for example, this is a transition for chain M from time t minus 1 to t, but you notice I'm conditioning it on Xm. So what is, what meaning, we already discussed this, right? So what meaning are you going to attach to these Xm's? Obviously, there are some unknown variables where they have to compute them. We have no idea what they are, but we're trying to mimic something. What are we trying to mimic here? A mixture of Gaussians. I don't. So remember, right? This K thing here is because I have different K states, so it's not, so that is there even if I do standard HMM, okay? But on each chain, I am plugging in this factor here, all right, that somehow needs to be accounting for what the effect of all the other chains on chain M. All right, so this is the only place that will allow me sort of to introduce local evidence in the model, all right? So in essence, getting rid of all of these things, right? We're going to do a variation approximation, getting rid of this coupling here, all right? So this will be a variable that accounts for the effect of all the other chains on chain M, okay? We have no idea what Xi of TMK is, so we're going to have to go and compute it, okay? So let's review fast. The joint variation approximation, or is written basically like this. Okay, this is for the initial state. So we have to do this for every chain from M1 to M. So this is for the initial state in every chain M, and this is for each chain M, the transition from t minus 1 to t. Okay, this is standard. What is different here is that we condition these things on local evidence C, okay? And the definition of the two variation distributions is what you see here, okay? This is the same as before, this is the same as before, this is now we plug it in, hoping to account for the mean effect, if you like, of all the other chains on each chain M. All right, so when you calculate, basically, you take the joint log likelihood here, the variation approximation can be written in a Gibbs form into some energy EQ, and this energy basically has an extremely simple form, all right? So obviously you are going to get logs of A and logs of pi. So these curly entities are basically these logs, okay? So let's see where all the terms come. Where is this term coming from? Let's start with this term. Where is this term coming from? Where is this term coming from? I mean, we only have, this is what we're looking, right? And I'm taking logs. What term here will give me this term? I can tell you again, this Xi curly is the log of this Xi. So where do I get that? Will it come from there? From this and there? When you take logs, okay? So this term comes from this term. This term will be coming from that term, okay? Where this curly A is the log of this A. This term here will come when you take logs from this term, and the incorporation of the logs from this term is accounted already in the summation here starting from t equal to 1, okay? So what is interesting is, if you look at the variation approximation, right, are the chains coupled? is there anything that says explicitly that this chain depends on all the other chains? And I remind you what coupling is. Coupling is the following. Look at that. So the actual posterior is e to the minus c, and E, all right, you can see all the states coupled together. Okay? We don't have that. So, the rest is algebra, all right? So what you need to do is, so we have the actual energy and the actual posterior, but we want to approximate it with this. And effectively what you need to do is, you need to form the KL distance between Q and P and minimize the KL distance with respect to what unknown variables. I'm going to assume that the transition probabilities and the initial probabilities are known, so the only unknown on this problem is going to be what? So in this model, what is going to be the only unknowns? The x's. So and again, the x's will be the evidence, an approximation of the local evidence coming to chain M from all the other chains. So that's the only unknown. All right? We're going to assume the parameters P and A here are given for simplicity. So if you do the KL minimization between the exact P and Q, and you do the algebra, I strongly recommend that you do it because I did it, and I may have some typos, maybe not, okay? So if you do this and you do it carefully, it comes out that you get an extremely simple formula that the update, this is a vector here, so I have removed the state k. The update of this vector c is this exponential of this WM matrix that comes, you remember, in the likelihood and the covariance minus 1. And this is the evidence, the data that is written like that, okay? And this delta is a vector that is formed basically by taking the diagonal elements of this matrix. The calculation is sort of a little bit tricky, but there is really nothing else except that you have to calculate the derivatives of the partition functions of the normalization factors with respect to x's. So that's sort of the only tricky part. You cannot allow basically to work with Q and P that are not anormalized. So you need to normalize them, and that's why you get these logs of ZQ and logs of Z. But apart from that, the rest is just history. This is a very simple formula, all right? And in normal circumstances, I will have asked you to write a little computer program to actually check this factorial hidden Markov model, because it really works. It really works. Even though it has lots of intuition there on the way you decouple the evidence, it worked quite well. Okay? And again, if you think about it, the only thing you have to do is a simple update formula. Okay? And the rest is basically, the rest is basically you have to do forward and backward message propagation the way we have done earlier with one chain and hidden Markov models. All right. I only have 10 minutes, so I can only start something. So let me. I'm going to go to a slightly different topic for those that are familiar with regression. Obviously, all of this will be posted on the website. So let me show you, and maybe we can actually finish it in 10 minutes. It's not a significant topic. So let's see if we can do linear regression using variational inference. Okay. Now again, I'm going to be talking about regression, assuming everybody in the audience knows what regression is. Okay? So, we basically have, we use some basis functions phi here to postulate a linear regression model. So you can think that the response of the system that I indicate here with tau is W transpose some vector basis functions that you can calculate at any point x plus some noise that is defined here by the precision beta. So basically I'm taking that the likelihood of the data is a product of Gaussians. It factorized over the IID data. Okay, so that's standard. Okay. Usually what you do in Bayesian regression, you're going to put some prior on W, given some precision alpha, all right? And then you're going to put some prior on alpha that is taken as gamma. Also, what you can do is you can make this a vector of alpha i's, and you can do relevance determination and all these very nice things for model selection. But right now there is only one alpha, all right? And so P of W given alpha is the prior, and P of alpha is another hyper prior on alpha. So this problem has, if you're asking for the posterior distribution of W, it has a very close form solution. We have done it, okay? And again, if you don't know it, it doesn't matter, because we're going to do an approximation from scratch. But I'm just telling you, with this, there is a posterior of W, okay? And not only that, there is a predicted distribution for T for any X. So, and when I mean a predicted distribution, one where, you know, you integrate W out. So basically an integral, if you can think of the likelihood at any location X, you know, times the posterior of W integral in W. There are closed form solutions to all of this, but we pretend we don't know any of this, and we really want to see if Bayesian inference will actually work. So in Bayesian inference, in any problem, all the time, you have to form the joint log likelihood. So what is joint is the data. These are the observations T. I don't indicate here the corresponding x's, right? So for a given x, you give a T, for another x, another T. So I only give the T's here, but remember, all this is conditional on the x's as well, okay? It's not important to mess up the notation. So the joint log likelihood is factorized exactly like that, right? If I know W, I know what is the probability of T, plus a prior on W given alpha, plus P of alpha, all right? And sort of the probabilistic graphical model, in a simple sense, looks like this, okay? A plate notation for the IID data, and basically W alpha and beta here. Beta, remind me, beta must be the hyperparameter coming inside that gamma distribution, okay? All right. So, variational approximations, 6 minutes to go. We're going to assume that Q of W and alpha factorized like that. We don't really have a knowledge of the exact solution. We pretend we never read the books. So we say, no, we want something that basically says that this is Q of W and alpha is Q of W times Q of alpha. We have no idea what these distributions will be. Okay. Standard formula, you kill it to death. And you kill it to death only if you try to do it by hand. Otherwise, looking at it means nothing. I remind you this. So the log of Q of alpha, for example, will be the expectation with respect to all the other variables. So what are the other variables here? What are the unknowns in this problem? So, you know, when we compute it is here, what are the unknowns? It's W and alpha only. So, so the expectation, or when I write the joint log likelihood, I'm going to be taking expectations here with respect to W. Okay? So, obviously there was a prior on alpha, there was a prior on W given alpha, and alpha doesn't come in the likelihood, so, you know, constant. So this is a gamma, all right? This, we took it as a Gaussian, so I'm taking the terms that depend on alpha, all right? The rest I don't care. And the expectation here is with respect to W, all right? So what distribution do you think you get for Q of alpha here? look, I mean, if this looks like a log gamma distribution, what do you think this is? What's the distribution for Q of alpha? It is obviously a gamma distribution, right, with updated parameters, because you can see log of alpha here, log of alpha, so you have A0 plus m over 2 minus 1, so the first coefficient is A0 plus m over 2, and Bn is equal to that, so Q of A is a gamma distribution, nothing fancy. You do the same thing with Q of W, the expectations now have to be with respect to alpha. So no surprise, actually this distribution comes to be a Gaussian, so this is the mean, this is the variance, and no surprise, by the way, every quarter where there is alpha, you get an expectation, not alpha, but the expectation of alpha. And for those who forgot, the design matrix is basically this matrix Phi that every row is the set of basis functions evaluated at each of the data points. Okay, so Phi is the design matrix. Okay, does somebody remember actually the exact answers to these problems? In other words, if we were doing exact inference, does the posterior look anything like that? This is like in Bishop's chapter 2, you know. Are any of these results look to you familiar for Bayesian regression? So, from, again, check me up, you know, in case I'm wrong, these results are identical basically with Bayesian regression, but only one difference. And that difference is, here there was an alpha, now we have the expectation of alpha. All right? And what was the other one? Here, you had W, well, I don't remember what is actually coming, but you can see, okay, so for sure this looks very familiar, but only having alpha here, okay? This you need to check it up, but you notice the coupling, right? To compute the distribution of variation of alpha, you need to know the moment W of the expectation W transpose W, so you obviously have to couple the two equations. Okay, so, all right, so actually the results, it says here from what I'm reading, they look exactly the same results you get with expectation maximization. The only difference is basically instead of alpha you use the expectation of alpha. All right, but we got those in a trivial manner, and that in some sense, you know, it tells you that all of these techniques at the end of the day are linked together. And I remind you that we already demonstrated that expectation maximization is a trivial subcase of the variational methods. Right? So it's sort of not a surprise that you get those results. If you want to get the predictive distribution, we have 1 minute to go. Basically what you will need is you will need to integrate the active times the posterior. And here, because we use variational methods, you don't put the exact posterior, you put the variational posterior. And this is the marginalization of the two Gaussians. This mean here is a linear dependence on W, so the solution is actually, we have seen it infinite times, is given analytically. So basically, both the mean and the variance, here's the variance, right, is given analytically. And again, instead of alpha, you get the expectation of alpha. If you want to calculate the lower bound, surprise, surprise, the lower bound comes to have a fantastic, wonderful analytical form, okay? Don't know, yes? And if you try to apply this to a simple polynomial regression, for example, you're asking, what order of polynomial m should I use? You know, obviously you can use whatever maximizes the lower bound, and in this case, if you do this problem, you can run this Python code, you can see m equal to 3 maximizes the lower bound, okay? I remind you, for those who study Bayesian regression, in Bayesian regression what you do is you do a similar plot, but instead of plotting the lower bound, what do you plot? The model evidence, right? Because we can calculate for this trivial problem exactly. Here the assumption is, yes, we can calculate the model evidence exactly, but this idea of L of Q is very powerful because in problems where the model evidence cannot be calculated, you can calculate L of Q, okay? So, so we will continue on that on Thursday and continue a little bit on this topic, then do something with Gaussian mixtures and some other interesting aspects. All right.